Back for another video lecture with me, Dr. Scott Spaniel, for Math 141 Statistics at Wharton College. This is the video for section 4.2, which could quite possibly be the last video lecture for the course, depending on how I have the course set up. So, welcome, and let's go and get started. So, in the last section, we talked about scatter plots and correlation coefficients. And if a correlation exists, then we can use least squares regression to find a linear equation to help us make predictions about what's happening between the two variables. So if you take out your chapter 4 note sheets, which can either be found in Blackboard or my math lab, depending on how the course is set up, and turn to page 7, we'll go and get started. So once we've created a scatter plot with linear association, so we only want to do this if there is a linear association, we may want to find a linear equation that can give approximate values for the response variable. The difference between the observed value and the predicted value is the error or residual. The least squares regression line is the line that minimizes the squared errors or residuals. It is the line that minimizes the sum of the squared vertical distance between the observed values of y and their predicted value for y hat, which is what we're going to use for our predicted value. So as we noticed in the, I mentioned in the last video, the calculator will tell you what those errors or residuals are, but that's what they're looking for. The equation for this is given with the following formula. B sub 1 times x plus b naught. You may have seen a similar formula, which is y equals mx plus b. In algebra, same idea, right? So b1 is the slope of the least squares regression line. And if we were going to calculate that by hand, it would be r times s sub y over s sub x. Okay? We're not going to do it by hand, but if you were, that's how you do it. And then the b naught is the y-intercept, and it's calculated by taking y bar, the mean of the y's, minus b1 times the mean of the x's. Okay. And then this just tells you what all those variables stand for. So that's what we're going to be looking for. So before we get into doing the calculations, let's talk about how we would interpret and what these different values would mean in an equation. So the interpretation of the slope. The slope represents what we expect the response variable to change by for a 1 unit change in the explanatory variable. Okay, so for example, if the slope was 7, then we would expect the response variable to go up by 7 for every 1 unit increase in the explanatory variable. So if the explanatory variable went up by 1, the response variable would go up by 7. So that's how we interpret the slope. The other thing we can interpret is the y-intercept. In order to do that, though, we have to answer 2 questions. Is 0 a reasonable value for the explanatory variable? To give you an example that we'll also use here in a minute, but looking back, was we did a problem in the last section with the weight of cars as the explanatory variable. Does it make any sense for the weight of a car to be 0 pounds? No. Okay, so in that case, we wouldn't be able to interpret the y-intercept. The other thing is, do any observations near x equals 0 exist in the data set? So are there any values for the explanatory variable near 0? If these things weren't the case, then any observations we made about the y-intercept would be outside the scope of the model. which refers to using regression model to make predictions for values of the explanatory variable that are much larger or much smaller than observed. Okay, so if we're not looking at values that are within our data set, we're outside the scope of the model. So, for example, if you looked at the weight of the cars we had in the last problem, and then you tried to, which were all in the 2,000 to 3,000 area, and you tried to use it to predict the miles per gallon for a car that weighed 10,000 pounds, that would be outside the scope of the model because it's not close enough to the data to make accurate predictions. And then in general, to interpret the y-intercept, we would say that it is the value of the response variable when the explanatory variable is 0. Okay, so let's go ahead and practice using those ideas and using these formulas. Okay, so after the first exam in a statistics course, Professor Catula surveyed 14 randomly selected students to determine the relation between the amount of time they spent studying for the exam and their exam score. She found that a linear relation exists between the two variables. The least squares regression line that describes this relationship is right here. Predict an exam score for a student who studied for X hours. So in this case, X is hours studied, right? And Y hat is score. So if we want to predict a student who studied for 2 hours, that means we want to let X equal 2. So we can plug that into the equation. And then we can use a calculator to find that value. So for example, here we could do 6.3333 times 2 plus 53.0928. Whoops, I got two of those backwards. 298. So this student would expect to get a score of about 65.6964. Okay, so that's the idea there. Then it wants us to interpret the slope. Okay, so to interpret the slope, well, the slope here is B1, which is 6.3333, the number being multiplied by X. And the way we interpret the slope is to say that for every one additional hour of studying, a student can expect their score to increase by about 6.3333 points. Okay? Whoops, sorry. I did this without switching screens, switching back. So here's what I was writing down while I was talking. So that's how we would interpret the slope. And then it says interpret the y-intercept if appropriate. So we have to ask these two questions. Is 0 a reasonable value for the variable? Is it reasonable that a student would study for 0 hours? Yes, right? That happens all the time. Is it a good idea? No, but it's reasonable. And then do we think there are values near that? Yeah, there probably are. We don't have the data set, but we do know that one student studied for 2 hours, or we at least predicted that, so that's probably within the scope. So we can probably do this. So the y-intercept was 53.0298, so B naught is 53.0298. So that means if a student studied for 0 hours, they should expect to get about a 53.0298 on the exam. Okay, so that's how you interpret those two things. And then a student who studied for 5 hours on the exam scored 81 on the exam. Studied for 5 hours, got an 81 on the exam. Is this student's exam score above or below average among all students who studied for 5 hours? So when they say the average, above or below average, what they mean is y hat. So what we want to do is we want to calculate y hat, for this situation. So that's 6.3333 times 5 plus 53.0298. So we can do that calculation. So I'll just change this one to a 5. And we get an 84.7. So the average is here is 84.7. So an 81 would be below average. Okay, so that's the idea there. So what I'd like you now to do is pause the video, flip to the next page and pause the video and try these problems on page 9, and then we'll go through them together, and then we'll talk about calculating these least square regression lines. Okay, so now that you've had a chance to try these, let's go ahead and talk about them. So, a student at Joliet Junior College conducted a survey of 20 randomly selected full-time students to determine the relation between the number of hours of video game playing each week and grade point average. She found a linear relationship exists between the two variables and the least squares regression line described here. Predict the grade point average of a student who played 8 hours per week of video games. So y hat would be negative 0.0526 times 8 plus 2.9342. Okay, so put that in our calculator. And so we get a grade point average of 2.5142. Okay. Then it asks us to interpret the slope. So the slope here is negative 0.0526, and the interpretation works basically the same every time. Okay. So if for every additional 1 hour per week of video game playing, a student's GPA drops by 0.0526 points. Okay. If appropriate, interpret the y-intercept. Does playing 0 hours per week of video games make sense? Doesn't sound very fun, but yes, it makes sense. And are there probably people who play close to 0 hours per week? Probably. So we can interpret it. So B naught is 2.9342. So a student who plays 0 hours per week of video games should have a GPA of approximately 2.9342. Okay, and then the last part is just like the last part on the previous problem. So we just need to, if we want to know if this student is above or below average, we just need to do y hat equals negative 0.0526 times 7 plus 2.9342. So find the GPA of this student, the average GPA of a student who plays for 7 hours. So we can just change this one to a 7. And we get 2.5667. So in this case, the student has a higher GPA than that, so they would be above average. Okay. So that's the idea there. Okay, so now in the next one, in his best-selling book, Moneyball, Michael Lewis discusses how statistics can be used to judge both a baseball player's potential and a team's ability to win games. One aspect of this analysis is that a team's on-base percentage is the best predictor of winning percentage. The on-base percentage is the proportion of time a player reaches base. For example, an on-base percentage of 0.3 would mean a player safely reaches bases 3 out of 10 times, or about 30%. For 2007 baseball season, winning percentage Y and on-base percentage X are linearly related by the least squares regression equation. Y hat equals 2.94x minus 0.4871. Interpret the slope. So the slope is 2.94. So for each 1% increase in on-base percentage, a team should expect a 2.94% increase in winning percentage. Okay, so that's the slope. For 2007, the lowest on-base percentage was 0.318, and the highest on base was 0.366. Use this information to explain why it does not make sense to interpret the y-intercept. Okay, so in this case, on-base percentage and winning on-base percentage would go from basically from 0 to 1, right? So these are pretty far from 1. This is 32% and this is 37%. So an on-base percentage of 0.000 would be outside the scope of the model. Okay, so that's an example of something being outside the scope of the model. 0% is a long way from 32%. Would it be a good idea to use this model to predict the winning percentage of a team whose on-base percentage was 0.250? No, for the same reason as above. That is outside the scope of the model. 25% is a long way below 32%. So that's pretty far below. That's 7 percentage points apart, which is farther than the range of lowest to highest on-base percentage. And then lastly, the San Diego Padres had an on-base percentage of 3.22 and a winning percentage of 0.546. What is the residual for San Diego? How would you interpret this residual? Okay, so residual, remember, is simply the difference between the actual value and the expected value. So we first need to find the expected value. Okay, so we can do that calculation. Okay, and we get y hat is 0.460 when I round to 3 decimal places like the other ones. Okay. So the residual is we take actual minus expected. So in this case, that's 0.546 minus 0.460. So that's 0.086. Okay, and so the way we interpret that is we could say that the San Diego Padres were 0.086 winning percentage above average. That's how much they were above the average. Okay, so that's the idea of how to use these lines and interpret things about these lines once you have them. Okay, so now what we want to talk about is we want to talk about finding these lines. Okay, so what we can do is same thing we did last time. In fact, you already know how to do this from the last video, right? Because to do one of the things in this chapter means to do them all. So we copy and paste our data from the homework, or in this case from our Google Sheet with the data in it. And then we tell it to do a linear regression, LIN, with x1 as the first variable and y sub 1 as the second. Okay, so those are our list. And so we have our values for this, and I can zoom in on it somewhere up here, zoom in on my data. So this is the same graph we used before. And if we want, we can see the residuals, and they'll put them in here, right? That's one of the things we talked about last time. So the residual is how far any of these dots are from their expected value from the line. But the part we want for this is simply the equation. So find the least squares regression line is what it was asking for. So the least squares regression line is y hat equals negative 0.0070x plus 4.44. I'm gonna round to 4 decimal places. So plus 44.8783. Okay. So that's all there is to get the line. And then you could do the same things we've just been doing with the other problem. So we could interpret the slope. And it's always appropriate to interpret the slope. So for each additional pound a car weighs, its MPG goes down by 0.0070 miles per gallon. And it would not be appropriate to interpret the y-intercept here because, as we discussed previously, this would be way outside the scope, right? It makes no sense for a car to weigh 0 pounds, so we can't interpret the slope. Okay, so it's not appropriate to interpret that slope. Now they want us to, Chevy Cobalt, while he's 2,780 pounds and gets 22 miles per gallon, is the miles per gallon of Cobalt above or below average? So we can do the same thing we did with the other problems. So y hat equals negative 0.0070 times 2780 plus 44.8783. Okay, and we can do that calculation in here. So that's negative 0.70. Okay. Whoops, I did that wrong. Negative 0.0070 times 2780 plus 44.8783. And so we get an expected miles per gallon of 25.4183, which in this case would be mean the Cobalt is less than that, so it'd be below average. Okay. Okay. And in fact, I think if you click on the line, maybe, let's find out. Yeah, you can also just scroll along here. So like, for example, and get an approximate. So 2780 is up here. And when the x value equals 2780, that would be our y value. So we can see that the Cobalt at 22 would be below average from that too, without having to get the actual value. But yeah. Okay. So, and then the last question. So I'll bring this back up. Oops, something's going to open I didn't want to open, but that's okay. Yeah, let's get rid of that. The last question here is, would it be reasonable to predict the miles per gallon of a Toyota Prius, a hybrid, and electric car? Why or why not? It would not be appropriate because this doesn't fit the scope. Because it's not the right kind of car. It's not a gas-only powered car, so there's other variables at play. So that's why that would not be appropriate. Okay, so to finish off this video, why don't you guys go and turn to this next page, pause the video, and try this problem, and then we'll go through it together. Okay, so now that you've had a chance to try it, let's go ahead and run through this together. So the data is in 4.2 problem 2 in the note sheet data set. Okay, so we can just copy and paste that into our ClassCalc and then ask it to do a linear regression for x sub 1 and y sub 1. And there's our equation. So our equation is the least squares regression line is y hat equals 1.69. I'm going to just round it 2 decimal places, x minus 142.47. And so let's look at the context here. So it says the American black bear is one of 8 bear species in the world. It is the smallest North American bear and the most common bear species on the planet. In 1969, Dr. Michael R. Pelton of the University of Tennessee initiated a long-term study of the population in the Great Smoky Mountains National Park. One aspect of the study was to develop a model that could be used to predict a bear's weight, since it is not practical to weigh a bear in the field. One variable thought to be related to weight is the length of the bear. The following data represent the lengths of 12 American bears. So here's our data. We can interpret the slope. The slope is for each additional centimeter in length, a bear's weight increases by 1.69 kilograms. Okay. Suppose a 149 centimeter bear is captured in the field. Use the least squares regression line to predict the weight of the bear. So that'd be y hat equals 1.69 times 149 minus 142.47. So we could go into our calculator and do that calculation. Okay, so that's y hat equals 109.34. And then what is the residual of the 149 centimeter from the table? Is this bear's length above or below average? So one option is we could go up here and get the 149 from the table, which is 85. So the residual would be 85 minus 109.34. Which is negative. So we went up to the table up here and found that the weight was 85. And this would be negative 24.34 pounds. So the bear is below average because it's negative. Another option is if we go to the graph of this and we ask it to show us the residuals and we look in the table, we can see that the residual for this bear was 24.96011. It's slightly different than the answer we got doing it ourselves because I rounded stuff off. But if you had left it alone, this is the answer you would get. Okay. So that's it for this video lecture, and most likely it's the last of the video lectures for this course. So have a good one. Make sure if you have any questions to send me a message on email or remind, and we can talk about any of this stuff together there. But otherwise, make sure you do all your assignments and have a good break.